Hello, everyone. Let's keep doing the reviews. Now, for the final exam review for non-calculus based Newtonian physics for the school that we're at, we are using three old exams that were three regular exams in times past. In fact, looking at the times past, I guess you could say I think everything was 2019, fall 2019 for the three exams. So there are three exams from fall 2019 that were regular exams, and the three of them together, 25 problems in each one of those three exams, so a total of 75 problems. Those three regular exams together of old comprise a good review for the final exam that you'll be taking at the end of this semester for the non-calculus-based Newtonian physics. We already did the exam number one, fall 2019 part of the review. Now we will do the exam number two, fall 2019 part of the review. And then the next video will have the exam number three, fall 2019 review. Those three exams, exams numbers 1, 2, and 3 from fall 2019 were regular exams, 25 questions each. Together, they are 75 questions, and they comprise a good review for the final exam that you're going to take in non-calculus-based physics, Newtonian physics, first semester. So I've told the students whom I have repeatedly that will be the case, so something to know. Those who are just studying this content, maybe want some review, hopefully this is a good review for you as well, even though you're not in my class and won't be taking the final exam. Let's talk a little bit. There are three problems in the beginning of this review for Physics 120, exam number 2, fall 2019. At the end of every one of the three videos, the first video pertains to exam number 1, fall 2019. This second video pertains to exam number 2, fall 2019, and the third video will pertain to exam number 3, fall 2019. At the end of each of those three videos, all of the answers from all of the old exams, exams number 1, 2, and 3, all those answers, all those tests with all the solutions will appear at the end of each of the videos. Even though each of the videos specifically talks about, one of the tests, and in summation, in aggregate, taken together in totality, exams 1, 2, and 3 will be spread out over those three videos, and together there are the review for the final exam. At the end of each one of those three videos, all of the content found in the exams as far as what is being asked of you and the solutions, all of it for exams 1, 2, and 3 will be at the end of each of the three videos. So something good to look at, I think. With this in mind, you guys, it says in the following three problems, the star systems are not necessarily the same. In fact, assume that they are all different from one another, but use t squared equals c a to the third for all, though c is potentially different in each case. Okay, so basically, guys, what they're talking about is, we're talking about Kepler's laws. We're going to do this. C is some constant. This is a to the third, which is analogous to a radius. It could be the semi-major axis, but for our purposes, we can assume that it's close enough, the semi-major axis is close enough to the radius. Number 1, two identical planets, P1 and P2, orbit a star in concentric circular orbits in the star's equatorial plane. P1 has an orbit of radius A1 equals 20 astronomical units. P2 has an orbit of radius A2 equals 30 astronomical units. And T2 for planet 2 is 30 years. What is the period of T1? So they're telling us a number of things, guys. Like I said, for the three that we're talking about this. We're talking about planets P1 and P2. And how's that going to play out? Well, okay. They're telling us that the radius of the orbit associated with P1 is 20 astronomical units. And we are not told what the period is. That's T1. That's what we're trying to find. For P2, we are told that A2 is 30 astronomical units. And T2, they did tell us, is 30 years. And this is the one that you got to find, you guys. In this case, trying to find that. Well, I'm going to deal with this reality and deal with ratios, and I think I'm going to be okay when I do that. So, again, it was said, this is part 2, video 2, film 2 of the final exam review, and it pertains to exam number 2, fall 2019. Later on, we're going to do part 3 of the final exam review, which will pertain to exam number 3, fall 2019. We already did part 1, which pertained to exam number 1 from fall 2019. So, okay, that's already been discussed with the students that are in my classes quite a bit, and also in this video, it is being mentioned. So, let's see what we can say here. Sorry about that. Okay, so as we look at it, a lot of ways we can go, but here's one way. T squared equals C over A squared. So T1 squared equals C times, and the A associated with that is 20 astronomical units. You take that to the third. The other one, T2, is 30 years. The C is the same because we're talking about they're revolving around the same star system. They're in the same, in the star's equatorial plane. So you got this. And the other one, you don't know what that is. But you know all this. Well, there's a number of ways you can do this. I've shown a number of ways to do it, I guess you could say. Let's just do it again. Take this divided by that. Take this divided by that. Take all this and divide it by all that. The C's cancel. So we got that. Forgive me, guys. There's actually there was more here. There's more data there than I seem to understand. Okay, let's try this. They want T1. They already told us. What was I talking about? My mistake, guys. They're telling me that we don't know what T1 is, obviously. We do know what this one is, and there were 30 astronomical units and 30 years. So let's see here, guys, exactly what is being said there. Yeah, absolutely, man. I got thrown off by the numbers here, guys. All this data is here. There's 4 pieces of information here, one of which is unknown. A1 is 20, A2 is 30, T2 is 30. And T1 is unknown. T1 unknown. C we're not going to worry about because we're going to do a ratio. So T1 is unknown. A1 is 20. A2 is 30, and T2 is 30. Okay, sorry, that's a better way to go. Do ratios here. T1 squared over 30 squared. Do a ratio of the left-hand sides. Do a ratio of the right-hand sides. The C's cancel, and you got 20 over 30. This is to the third. This is to the third. There's a lot of ways we can go with this. T1 squared is 30 squared times this. Well, this is kind of interesting. There's a lot of ways to go here. Here's one way, it's maybe easy. Here's what's 20 over 30? Yeah, you got to remember, guys, if you say 20 to the third over 30 to the third, that's the same as 20 over 30, the whole thing taken to the third. Well, 20 over 30 is 2/3. Take that to the third. 2 to the third is 8. 3 to the third is 27. Uh, 30 squared is 900. I mean, there's a lot of song and dance you can do with this thing, I guess you could say. 900, there's a 9 in here, so it's 100. 100 over 3 times 8, it's 800. 800 over 3. And, what you're looking at there is what the T1 would be. Well, you kick this thing around a little bit, you're getting it down to this, which is what I said earlier, which is what I said earlier. And T1 is the square root of, T1 is the square root of T1 squared. True. And if T1 squared if T1 squared is equal to 800 over 3, get the square root of each side, and you're going to find what T1 is. T1 is 16.33 years. $16.33. That makes sense. Because look, there is the square of the period is directly proportional to the cube of the radius in which the orbit is taking place. If it's a big radius, it's going to be a big time. If it's a small radius, big period, small radius, small period. So this is a smaller radius in which the orbit's taking place. 20 compared to 30. This is smaller. Should be smaller than the 30 then. So the 16.33, I guess it makes sense that it would be doing that. All right, guys, that's basically the way the arguments take place. Let's kind of take it. Let's keep going. Let me erase this and we'll get to the other one. Might be easier to kind of start at a certain point and then go for it. Let's leave this. Let's compare the planets. I guess there's a lot we can say here. All right, well, I mean, they're going to say a few things here. There's going to be, we're going with this, there's going to be an A1, there's going to be a T1, there's going to be an A2, and there's going to be a T2, and we're going to find out what they're going to ask us to do here. So for number 2, two identical planets, P1 and P2, orbit a star in concentric circular orbits in the star's equatorial plane. We've said that before, same kind of scenario. For number 2, two identical planets, P1 and P2, orbit a star in concentric circular orbits in the star's equatorial plane. P1 has an orbit of radius, A1 is 10 AU. And period, 15 years. P2 has an orbit. P2 has an orbit of A2 in a period of 20 years. Didn't really tell us what this one was. That's the one we got to find. What is the radius of the orbit of P2? It's the same kind of logic, you guys, when you're playing this game here. You're going to say, okay, well, T1 is 15. I'll square it. C is something. The A associated with it is 10. We'll be cubing that. The other one is 20. We don't know what A2 is. And, okay, let's do the math from there. I mean, let's divide these two. That's the same as the ratio of exponentiated quantities is the exponentiation of the ratio. You can bring, if you're going to take the ratio of two things that are exponentiated, you can just take the ratio before the exponentiation and then exponentiate. C divided by C is out of there. You got 10, got 10 to the third over A sub 2 to the third. Well, there's a lot going on, guys. You can do. I do it a little differently, I think, in some of my notes, but it's essentially the same argument. So we're not going to lose too much sleep on this. 15 over 20 reduces to 3/4. I mean, if you can make a move like that, it's not a bad move to make, I guess. 10 cubed is 1,000. This is this. And, there's just a lot you can do here. This you can go 9/16. This is 1,000. This is A sub 2 to the third. Multiply by A sub 2 cubed on each side, and then multiply by the reciprocal of this on each side. And you're looking at A sub 2 cubed is equal to 1,000 times the reciprocal of 9/16. And, wherever there's a lot going on here, guys, you can make the move anytime you want. I mean, this right here is 16,000 over 9. Get an answer there. Take the cube root of both sides. Let's see where this is going to go. A sub 2 is 12.11 AU. Again, this is believable. We did it right. We didn't do anything wrong here. We certainly did it right. What's going on here? What did we do? Well, I'm saying A sub 2 is 12.11 AU. That makes sense. This is 10 AU associated with that kind of a period. If the period is larger than that, you're talking about a bigger radius, associated with the orbit. If it's a bigger period, there's a bigger radius. The radius, 12.11 AU, is bigger than 10 AU. So it's believable. Okay? Just be careful how you do this stuff. People try, it's easy to get thrown off. Three. Here we go again. Let me erase this and we'll do it that way. It might be easier to just see the stuff fresh when we're talking about it. We'll see what they're talking about vis-a-vis a lot of this stuff. For number 3, two identical planets, P1 and P2, orbit a star in concentric circular orbits in the star's equatorial plane. We have been there. For all 3 of these problems, it is the same introduction. P1 has an orbit of radius A1 and period T1. So we've got this P1, P1 has A1 and T1 associated with it. And P2 has an orbit of A2 and period T2. So okay, sounds good enough to me. Given that A sub 2 over A sub 1 is 1/8, what is the ratio of the period? So they're going a little different on us now. They're saying if they're telling you this ratio, if A2 over A1 is 1/8, what is the ratio of the periods? T2 minus T1. They're looking to find that. Tell you what I'm going to do. We've got T1 squared C A1 cubed T2 squared C A2 cubed. That's a true story. Tell you what, since they're going, there's nothing wrong with that. I tell you what though, since they're got A2 on top, A1 on the bottom, T2 on top, T1 on the bottom, aesthetically it might be better to just say, okay, let's put a 2 here. Let's put a 2 there. Let's put a 1 here. And let's put a 1 here. Let's go like that. Let's do these two ratios. We've got T2 over T1 squared. It's T2 squared divided by T1 squared, which is the same as the quantity T2 over T1, the quantity squared. Divide here, the C's cancel, and you got A2 over A1, the whole thing cubed. So let me just explain that again in case there's any kind of disparity here. If you get this, the ratio of exponentiated quantities is the same as the ratio. The ratio of exponentiated quantities is the same as the ratio being exponentiated. The ratio of exponentiated quantities is the same as the ratio itself being exponentiated. So if it's like this, you can pull out the exponentiation like this. If it's like this, you can pull out the exponentiation like that. Okay? This is what we got. That's not bad. That tells us about as much as we need to know. Tells us about as much as we need to know. A2 over A1 is 1/8. Don't know what this is. I'm trying to find it. But A2 over A1, they told me is 1/8. And that's going to be cubed. This is squared. This cubed is going to be 1 over 8 times 8 times 8. Well, 8 times 8 is 64. Times 8 is 512. Good enough for me. Once you get it down to here, get the square root of both items. T2 minus T2 divided by T1 is going to be, get 1 over 512. At the end of the day, guys, it is going to be 0.0442. And there we go, guys. There we go. Let's go to problem number 4. Let me erase that. Let's take it. right, guys, for number 4, they are saying a couple things here of interest. For number 4, the horizontal surface on which that block slides. So they got, you guys should have this in front of you. If not, you'll see it at the end of the video, but let's do a drawing anyway. Spring constant K. This thing right here is flying right at it. Magnitude velocity V. This is 2 kilograms. Let's see what's going on here. So you're associated with the spring. The horizontal surface on which the block slides is frictionless. The speed of the block before it touches the spring is 50 meters per second. How fast is the block moving at the instant the spring has been compressed 30 centimeters? K is 1,200 newtons per meter. So if the spring has been compressed 30 centimeters, it ain't going to be going as fast as it was going earlier. How fast was it going earlier? The speed of the block before it touches the spring, we'll assume a constant speed, no acceleration at that point. 50 meters per second is what it's doing before it hits the spring. It's going 50 meters per second, not accelerating, going 50 meters per second before it hits the spring. Once it hits the spring, it compresses the spring. Well, we know what happens when it compresses the spring. It's going to slow down, at least somewhat. There is a spring constant, 1,200 newtons per meter. So how fast is the block moving at the instant that thing's been compressed by that amount? Number of ways to go here, I guess you could say. We talk about energy considerations, and if we play it right, we should be able to use initial energy considerations and final energy considerations. The initial energy considerations is this thing is moving. I put VI here. I might as well put V. It doesn't matter. The initial is VI, which is the same as V. I could say in this case, VI and V are the same. So let's not have any confusion on that. 1/2 mVI squared is what's initially happening. There's no spring, no anything going on. There's just kinetic energy. All that kinetic energy is going to go into potential energy when it compresses the spring, and what is left over will be some measure of kinetic energy. Well, that's really what I want. I want the VF. This one right here, guys. I want that right there, and let's just figure this out. Well, let's play some mathematical games here. Let's get this all by itself, and it's 1/2 m. 1/2 m VF squared is 1/2 m. Just doing some mathematics, solving for that on its own, or getting it on its own. They're using meters, so the centimeters are going to get converted to meters. Let's multiply by 2 on each side and divide by, let's multiply all of this by 2 on each side and then divide by m. This is the argument. We have this. Square root each side. Follow the rules. Don't go, we're not inventing our own mathematical rules doing this. We're just doing the job. We got this. Probably the most important part of the conclusion you're going to reach. Plug in all values and you should be fine. So what does that mean? Well, what I just said. I mean, but you got to be careful. What's what? The mass is 2 kilograms. The mass is 2 kilograms. K is 1,200. X is in meters, 0.3 meters. V was, they were telling you right off the bat, was 50. Let's maybe just play it safe. Let me just walk you through it too much. You got 50 squared minus 1200 divided by 2. Well, we know where that's going. This is where you don't make the mistake. If you do, you'll get the whole thing wrong. 30 centimeters is 0.3 meters. This is newtons per meter. This is kilograms. This is meters per second. This answer has to be meters per second. You got to have meters in that place. That's the big move you got to make. Make sure the 30 centimeters comes out to here. At the end of the day, guys, you got VF. VF is 49.46. Meters per second. Well, it's kind of interesting. Didn't lose a whole lot of speed, but it did lose some speed, right? Which is understandable, which we thought was going to happen. Okay? All right. That's that. What is the momentum of the block at maximum compression of the spring? So, okay, they're making us, they're telling us what's going on here, I guess. Well, okay, they didn't tell us that before, but that's all right. It doesn't matter. I mean, we don't know what's going on with this spring. From what we understand, the spring itself is 30 centimeters long. It's 0.3 meters long. It'll go to the maximum. And it's going to, at that point, it's whatever. There's some kind of collision is going to happen because it's certainly not stopped. It's not being stopped by the spring, that's for sure. The big question being asked here, and this is number 5, you guys. The big question being asked right here is, what's the final momentum? Well, in terms of magnitude of momentum, it's mass times VF. That's the final momentum. It's 2 kilograms times 49.46 meters per second. It's going to be 96.92 or 91, depending. There might have been some other things going on with the calculator, but nobody's going to nickel and dime me at this point. If it's 0.91 or 0.92, should be all right. Now they're saying that's the math. Well, okay, time out. Well, actually, time out what I said earlier. I don't know that the spring is 30. I shouldn't have said what I just said within the last few minutes. I don't know that the spring is 30 centimeters long. It could be much longer than that. The amount of compression that took place under which we are regarding this problem, we're saying it compressed to 30 centimeters. It's still going to keep moving. Now, if the spring's not that long, it's going to collide with the wall, but we don't know how long the spring is. We'll say at the 30 centimeter point what was the actual. So it's not necessarily that it was only 30 centimeters long. It's just the amount by which we are making an accounting of what's going on. Hey, at that 30 centimeter mark, by the way, how fast is it going and what is its momentum? That's kind of where it's going. So be aware of that. I should have spoken differently regarding that. There is got a little bit of room. I don't know that I do or not, but let's try to talk about a little bit more room here, if I got it. Let's look at number 6. Number 6 is saying a ball moves with a constant speed of 50 meters per second around a circle of radius 0.625 meters. What is the period of motion? Hint, for this calculation, you need to know the circumference of the circle. Okay. They're saying that it's going around with a velocity or magnitude of velocity of 50 meters per second. The radius of the circle around which this thing is going is 0.625 meters. We know that distance covered is average speed times time. Now they want to know how long it takes to get around this thing. You understand distance equals speed times time. If you divide by v on each side, you got distance over v. Yeah, the distance is 2 pi r divided by v. Here goes. 2 pi times the radius of, make sure the units are meters, seconds, kilograms, meters per second, meters per second for acceleration, meters per second, whatever. Make sure everything's okay that way. Divided by 50. Okay. When you do this, you're going to get 0.0785 seconds. And that is the case, guys, and that's what it's looking like when we do that. 0.0785 seconds, that comes out to 0.079 seconds. Let's go to 7. Let me erase and let's take it from there. Okay, guys, let's go to 7. A car traveling at 50 meters per second follows a curve in the road so that its centripetal acceleration is 15 meters per second per second. What is the radius of the curve? So there's a centripetal acceleration of 15 meters per second associated with this. The car itself is going at a magnitude speed of 50 meters per second. We know that A sub c is equal to v squared over r. I don't know if I used a small r or big R. That's not really a big deal, actually. And of course, I used a small r when I just wrote big R. That's not a big deal. But either one. I mean, frequently you see it written with a big R. But we've got this. Go here. Multiply by r on each side and divide by A sub c. We've got 50, make sure the units are MKS system of units. We've got 50 meters per second squared over 15 for the acceleration. 50 meters per second squared over 15 meters per second per second. There are a number of ways to go here. This is going to be 2,500 over 15. The 5 goes into 2,500 from the 15, goes in 500 times, so it's 500 divided by 3. That's going to be 167 or so, 166.67. So let's see here. See what they actually got. That is what they got. 166.67. Radius of curvature in that vicinity. Yeah, makes sense. If the acceleration were, I don't know what to say, if the acceleration were, let's say, 4 times this, not 15 meters per second, but 60 meters per second, the radius of curvature would be 1/4 that. It'd be 40 something, not 160 something. And that makes sense. The tighter the turn you take is indicative of a higher centripetal acceleration taking place for that to happen. So that's 7. We'll talk about 8. 8, a robot is whirling a stone around its head by means of a rope. The rope makes 3 complete revolutions every second. And the magnitude of the tension in the rope is F. The robot then speeds up the stone and making the radius of the circle 5 times the original radius. And so that the string makes 6 complete revolutions every second. What happens to the tension in the rope? Ignore gravity and the mass of the rope. This is definitely of interest. So let's see what we can say regarding this. We got to get some kind of a gut feeling as to what's going on here, guys. Well, the centripetal force is mass A sub c. F sub c is mass v squared over r. The stone in both scenarios is the same stone. Just what else is going on to make a comparison? A robot is whirling a stone around its head by means of a rope. So the mass is the same. Now let's see what happens here. A robot is whirling a stone around its head by means of a rope. The rope makes 3 complete revolutions every second. It's going at a speed. Let's say the 3 complete revolutions is, let's talk about the 2 scenarios here. What happens to the tension of the rope? Let's say like there's an initial tension, and we could also say tension is F sub c for the rope. There's an initial tension and there's a final tension. And, well, I mean, they didn't tell us how big the stone was, but we're going to say that the tension is the same as the centripetal force. In both scenarios, the stone is the stone, and it's the same stone. In the first scenario, the initial scenario, they're telling us that the rope makes 3 complete revolutions every second. So I'll tell you what I'm going to do. There's different ways this gets said. Let me try to follow. A lot of ways to go here, I guess you could say. See how we could say this, I guess you could say, guys. Let me just try to make this make a little bit of sense for us. There is, the rope makes 3 complete revolutions every second, and the magnitude of the tension in the rope is F. So, for the first scenario. So this tension, initial tension is F. This tension right here, it's the final tension, I guess you could say, which is the same as that. So, okay, let me try to think, guys. There's a number, I'm trying to follow. There's so many ways to go here. Let's try to make it make some sense. In the first scenario, and I'm using 1 and 2 on these. 2 is the second scenario, whereas I used I over here. Okay. Well, let's see what we can say. Either one works out okay. If you're gonna do that, let's, for this right here, I'm trying to use what I used in the book, and this is turning into a little bit of a mess, but that's not something that we cannot handle. Let's go here. F final, which is the tension final, we'll call F2. And the initial, this is F1. So it's a little bit of a mess. But basically, let's just say that F2 is associated with the final tension. F1 is associated with the initial tension. Let's write it like that. I'm just going to try to make it look like the stuff I wrote on paper, guys, so it's not too much of a mess for us. They are basically saying there is, there's the situation of the final situation, which is going to be F2 is going to be equal to m v2 squared over r2. True. F1 is going to be m v1 squared over r1. Again, this is the final tension. This is the initial tension. Sorry I wrote, again, there's variables all over the place here. I got into this, we did it, but the tension's the same as the force centripetal. The force centripetal in the final scenario, when the robot speeds everything up, the final force is the final tension, and that the final force, which is the final tension, we'll call F sub 2. The initial force, which is the initial tension, we'll call F sub 1. This is M1, V2 squared over R2, and this is M1 V1 squared over R1. So we've got these two. We've got this right here, and we've got this right here. Now, hopefully this is making a little bit of sense, guys. Basically, you're comparing two scenarios here. The only thing common here is the mass. The stone doesn't change. What happens is, if you do a ratio of these two, you end up getting the final divided by the initial, which is m v2 squared over r2 squared, m v1 squared over r1 squared. Not squared. None of the r's are not squared. I'm sorry. Again, we're coming back to, obviously we're doing this, and that's coming from this. So there's no r squared. Sorry about that. All right, guys. As you're looking at this, let's do something about it. When you do it, the m's will cancel. You'll get V2 over V1 squared. You'll get R1 over R2. And that's a big move. I mean, at this point, when you make the moves right, if you go to here, you should be getting all this from past conclusions that we've drawn. Okay? The m's are constant in both scenarios, both time periods. It's the same stone. V2 is different from V1. R2 is different from R1. V2 squared over V1 squared is V2 squared over V1 squared, or take the exponentiation on the outside. R1 on the bottom here flips up, and you get this. Okay? So this is where it's all going to happen. Well, that's good. I mean, they're telling us a number of things here. So let's be careful what they're telling us, I guess you could say. The rope makes 3 complete revolutions every second, and the magnitude of the tension on the rope is F. The robot then speeds up the rope, and making the radius of the circle 5 times the original radius, so that the string makes 6 complete revolutions every second. What happens to the tension of the rope? Okay. A lot has happened here. I'm going to try. I did different things here. I don't know. I can follow my notes or I cannot follow my notes, I guess you could say. I will say that the rope makes 3 complete revolutions every second, and the magnitude of the tension of the rope is F. That's the initial situation. 3 complete revolutions. The robot then speeds up the stone and making the radius of the circle 5 times the original radius, so that the string makes 6 complete revolutions every second. If this is very, I'm trying to think of a good way to say this. If it's making 6 complete revolutions per second as opposed to 3 complete revolutions per second, the period has been cut in half. True. It is going relatively very fast. True. More fast than you think. Because it's not just doing 6 complete revolutions every second in the final scenario. It is doing 6 complete revolutions every second in the final scenario, as opposed to 3 complete revolutions per second in the first scenario. Yeah, it's not a ratio, however, of 2 to 1. The radius has been made bigger by a factor of 5. That means it's covering 5 times the distance per revolution that it covered earlier. It's basically going, so I mean that's a big thing. So what happens is, I said it different ways here. I get the R1 over R2. They're saying R1 is R1. R2 is a radius of 5 times that. That's this. For the speed being squared, it's 6 times 2 pi r. The r is 5 times more, 5 times bigger radius than was going on initially. The other one was going 3 times 2 pi r, and that r is just r sub 1. That's the big move. That's the big move in all of this, you guys. That this right here, when you sped it up, it's 5 times the radius of what it initially was. 2 pi, the r now is 5r1 when you've sped it up in the last scenario, in the end scenario. It's 5r1 for a radius, 2 pi times 5r1, and it's doing it 6 times per second. Here it's doing it 3 times per second, but it's worse than that, I guess you could say, because it's only dealing with a radius that's quite small compared to the radius being dealt with here. This is really fast. 6 times 5 is 30 times 2 pi r1. This, look at it carefully. This is 6. Go 6 times 5, just those two. Go 6 times 5 is 30. 30 times 2 pi r. 6 times 5 is 30 times 2 pi r1. This is 3 times 2 pi r1. 30 2 pi r1 divided by 3 2 pi r1 is a ratio of 10 to 1. It's really going faster. It's going 10 times faster than it was earlier. Yeah, don't forget, you're going to square it as well. Well, yeah, but you don't have quite the same centripetal acceleration that you could have had if you kept the same, I don't know, maybe kept the same radius and maybe done this another way and then done this ratio for speed. The fact that it's a bigger radius is going to take away from the centripetal acceleration. R1 over R1 is just 1. This is 1/5. This is just 1/5, guys. So what happens here at the end of the day is the ratio final over initial is going to be this. This is 100. 100 times 1/5 is 20. Basically, F2, final scenario, multiplied by F1 on each side, is going to be 20 times the initial scenario. F2 is basically, let's call F1, you can call it F if you want. If F was the original force, what did they say it? Did they actually say that here? Yeah, they said F. So F is, yeah, forgive the, this is, there's the F2 at the end. And then there's F1, which is equal to F. They were originally telling us there was an F there. So we got that. So the F2 is equal to that. The person better be pretty strong because they need to exert 20 times the force of what was originally being exerted for this to all happen. Okay? Let's go to number 9. Let me erase from there, and we'll kind of take it from there. All right, guys, keep going. Number 9, a 100 kilogram ball. Number nine, a 100 kilogram ball attached to a cable is rotating in a horizontal circle of radius 20 meters. If the ball revolves 5 times per second, what is the tension in the cable? It's kind of an easier version of what we just saw, guys. They're telling you, the force centripetal is going to equal the tension. It's going to be mass velocity squared over r. It is a 100 kilogram ball. It's attached to a cable and is rotating in a horizontal circle of radius 20 meters. If the ball revolves 5 times per second, what is the tension in the cable? Five times 2 pi r. It revolves 5 times per second. Kind of what you're looking at. Let's take it. We've got the tension's going to be 100. There's a lot. Let me see exactly how I did it. I mean, there's no real issue here on this, guys. At this point, it's kind of a done deal. We know how to go. It's per second, per 1 second. 5 times 2 times pi times r, right? Okay, so what you got here is, you got 5 times 2 times pi times r there it is. The rest is just math. At that point, I mean, take 20 and square it, and then divide it by 20. You just got a 20 left over. So what you got here is this. You got this. You got this. Not exactly the way I wrote it on the thing, and you got a 20 right here. Forgive me. If this is being squared, the 20 is squared. The 5 is squared. The 2 is squared. The pi is squared. The 20 was being squared, but then you divided it by 20 and you got to here. That's pretty interesting. 5 squared is 25. 5 squared is 25 times 4 is 100 times 20 is 2,000. This squared is about 10. 2,000 times 10 is 20,000. About 2 million. And that's about right. And it comes out, comes out ballpark of 2 million there, guys. It comes out 1973920.88 newtons. That's, like I said, you look at it, you say, okay, where is that? Okay, it's going to be about 1.97. How consistent is that with the answer? And I said it was going to be in the ballpark of about 2 million. And that is in the ballpark of 2 million, guys. Sure is. So we got that. That's 9. 10. 10. A planet has a mass that is roughly 300 times that of the Earth. It's a very massive planet, guys. A planet has a mass that is roughly 300 times that of the Earth, and a radius equal to 9 times that of the Earth. How many times larger is the acceleration due to gravity on the surface of this planet compared to that on Earth? How many times the size of G on Earth? How many times more is it than G? Well, there's a number of ways to go. Let's see what we can say. See if it makes some sense to us. The force of gravity on the planet compared to the force of gravity on Earth is actually a ratio of the G's. The G force, the G acceleration on the planet, G sub P, and the G that we're used to, just G, we'll call it G sub Earth. For anything that's on there, the mass doesn't change. It becomes GP over GE. This is what we're looking for. This is what we're looking for. Let's talk. Force of gravity on the planet, planet P, is the mass of planet P times the mass of the object or person on that planet divided by, it's the universal law of gravity, guys. It's this. And you're going to compare that to what's going on Earth. Okay. When you do the ratio, the G's go, the small m's go, and what we end up getting is big M sub P over big M sub E, right there. We got RE squared over RP squared. And yeah, sounds good to me. That's the way it's going to work. All this is about that. This is the thing you're going to find here. You're going to find it right here divided by right here. And that's going to be how that's how it compares. That's GP over GE. Okay, didn't they tell us this is 300 times that of Earth? Didn't they tell us this got 9 times what Earth has? Interesting. That's 300 over 1 times RE squared cancels. The 9 squared on the bottom is 81. Between 3 and 4 times more when we actually do it. So this right here, we're We're going to get that answer, and it's going to be 3.7. 3.7 times what GE is. This is a bad place to do the high jump or to run or do just about anything else. Everything is going to be 3.7 times heavier. The acceleration due to gravity when you drop something is going to be 3.7 times more than what it is on Earth. And that's 10. That's 10. Let's go to 11. All right, let's talk real quick on that. All right, well, let's look at number 11, you guys. A concrete block is pulled 1,000 meters across a frictionless surface by means of a rope. The tension in the rope is 300 newtons, and the net work done on the block is 90,000 joules. What angle does the rope make with the horizontal? There's a lot going on here, guys. I didn't, in some classes I've emphasized the dot product more than in others. We got to have some sense of it. Work is the force vector dotted with the displacement vector. Now, what does that mean? For our purposes, that means F times D times the cosine of theta. Sounds good to me. I mean, if I want to do this, let's find out the cosine of theta by going W divided by FD. If I want to solve for this cosine of theta, I'm going to divide by FD on each side, and I got to here. What does that equal? Well, okay, that equals, the work they're claiming got done is 90,000. The force is 300 times 1,000. That's 90,000 over 300,000. Forgive me, I didn't do enough of that. Yeah, there it is. Okay. That's a lot. I mean, what I can do is 30,000 goes into here 3 times. 30,000 goes into here 10 times. The cosine of theta is 3 over 10. Cosine of theta is 0.3. Get the inverse cosine of cosine theta. That's the same as inverse cosine of 0.3. And theta equals 72.5. Absolutely. 12. A projectile is launched with a momentum. A projectile is launched with a momentum of 10,000 kilograms per meters per second, and it has 150,000 joules of kinetic energy. What is the speed of the projectile? This is a neat question. It's not too bad. For 12, it's saying a projectile is launched with a momentum of 10,000 kilograms. So, for 12, we're saying the momentum, that's m times v, is 10,000. Everything's MKS, so I'm not worried too much about the units. The kinetic energy, which is 1/2 mv squared, same v under consideration, is equal to 150,000 joules. So P is this guy, KE is this guy. What is the speed of the projectile? There's a lot you could do here. One of the things you could do, a number of ways you could play the game, I guess you could say. You could take, okay, let me take kinetic energy, which is this, and let me divide it by mv, by momentum. The m's cancel, the v's cancel, or partly cancel, you got this. But wait a minute. Isn't that 150,000? Isn't this top one? Look at mv, look at 1/2 mv squared. They look kind of alike. Do a ratio here. The half is going to stay, the v is going to stay, but the other v cancels, and the m cancels. And you got this. You got something like this going on. And you get the other one, the mv on the bottom is 10,000. Wait a minute. That's really how the whole thing's going to go. 1/2 v. I mean, I don't know. You can do a whole bunch of things here. 10,000 goes into 150,000. Forgive me. Yeah. 10,000 goes into 150,000 15 times. 10,000, you pull a 10,000 out of here, it's 15 times 10,000. Pull a 10,000 out of here, it's 1 times 10,000. So it's 15 times 10,000. It's 1 times 10,000. You know where I'm going. It's 15 over 1. Multiply by 2 on each side. Well, after all that, multiply by 2 on each side, I'm getting this. For number 12. Um, 13 follows, well, again, we got the V for it. Basically, if you're careful, for number 13, they're saying a projectile is launched with a momentum of 10,000 kilograms times meters per second and 150,000 joules of kinetic energy. What is the mass of the projectile? Wait a minute, they gave us all this data before. The thing has a momentum of 10,000 kilograms meters per second, momentum of 10,000 kilograms meters per second, and has kinetic energy of 150,000 joules. We just found what V was. I wonder what the mass of the things. Well, it doesn't matter. I can use either one of these guys. I can use this one, or I can use this one. It's probably the easier one to use. The momentum, guys, is mv. You divide by v on each side. The mass is, momentum is mv. If you divide by v on each side, you got this. Momentum is, they told me 10,000. They said the velocity was 30, or magnitude velocity was 30. That's 1,000 divided by 3. The mass makes sense. I mean, it comes over here. The mass is 333.3 kilograms. 333.33 kilograms given the explanation that was given before, and that's number 13. Let's go to 14. Let me erase some of this and just keep going. Okay, let's keep going, guys. 14. Joe is running at 8 meters per second. If Joe weighs 900 newtons, what is the magnitude of his momentum? Joe's weight is mg. Joe weighs 900 newtons. I don't know what his mass is, but I know this is 9.8 meters per second per second. In plain English, guys, if they give you this and W is weight, the mass divided by G on each side, the mass is going to be this. 900 newtons divided by 9.8 meters per second. That's all this is. That's all this is. Divide by, take 900 newtons and divide by 9.8 meters per second, and we'll get what the person's mass is. Once we got his mass, we'll find his momentum. His momentum, magnitude of momentum, is mv. We are told he's running at 8 meters per second. His mass is going to be what it is. I mean, it's going to be 900 divided by 9.8, and from there we can figure it out. I mean, 900 divided by 9.8. If you go for it, we are saying what the person's momentum is. It's going to be 934.7 kilograms meters per second. That's 14. 15. A 3-kilogram steel ball is dropped straight down onto a hard horizontal floor and bounces straight up. The ball's speed just before and just after impact with the floor is 30 meters per second. Determine the magnitude of the impulse delivered to the floor by the steel ball. Impulse, the magnitude of the impulse is the change in momentum. It is a 3-kilogram steel ball falling at 30 and rising at 30. $30 minus a negative 30 And that's it. That's the impulse. For number 15. 16. A baseball of mass m, small m, initially moving at velocity minus v. V is a positive quantity. So negative v is velocity, means just it's going in a particular direction associated with the negative direction. But v is a positive quantity. So a baseball of mass m initially moving at velocity negative v, where v is a positive quantity, is struck by a bat so that it acquires a speed of positive v. If t represents the duration of the collision between the bat and the ball, which one of the following expressions determines the magnitude of the average force exerted on the ball? The best way to look at that is the force average is change in momentum over change in time. The ball, mass m, was initially moving at negative v, and then goes, it's going negative v one direction, and it goes exactly in the opposite direction with the same magnitude velocity, but it's completely changed. It was going one direction and goes exactly the opposite direction. So this is how you're going to set that up for change in momentum over a time period. And what did they say? I think they probably just said delta t on this, if I'm seeing this right. Well, they didn't say delta t, but I could say delta t. We can look at it like this, kind of have it in the back of our mind. Delta t and t can be synonymous if we're mindful of various things. So let's see what we have here, guys. We got F right here. V minus a negative v is 2v. 2v times m is 2mv. Divided by delta t, or divided by t. And I think in the actual the actual exam itself, they don't say F equals, but certainly it is F equals. They're just talking about this. That is 16. 17. A 5-kilogram steel ball collides head-on with another object so that its velocity changes by positive 80 meters per second in 0.02 seconds. They didn't really tell us too much. They just said it's a 5-kilogram steel ball. It collides, that 5-kilogram steel ball collides head-on with another object so that its velocity changes by positive 80 meters per second in 0.02 seconds. What is the magnitude of the average force with which the ball was struck? The game they're playing here, guys, and that's 17. Is saying the force on average is going to be delta P over delta T. This thing underwent a momentum change. Well, it underwent a momentum change. Basically, if it changed, if the M, VF minus VI, I guess you could say, over delta T is equal to, well, let's look at what it's equal to. It's a 5-kilogram steel ball. That's 5. The change here, they told us, was 80. And the delta T, the time over which it took place, is 0.02. So this is what this means. And what that means, and that's basically what we're trying to find. but this is where it's happening. It's 5 kilogram steel ball, velocity changed by a positive 80 over a time span of 0.02 seconds. The rest is math. You grind this out, and you've got, as an answer, 20,000 newtons. It's a lot. It's an awful lot. And that's 17, you guys. All right, let's keep going. Okay, let's keep going. So that was 17. That was 17. Number 18. The head of a hammer, number 18, the head of a hammer, mass 5 kilograms, moves at 25 meters per second, moving at 25 meters per second. So the head of a hammer with a mass of 5 kilograms, moving at 25 meters, strikes a nail and bounces back with the same speed after an elastic collision lasting 0.150 seconds. 0.150 seconds. What is the magnitude of the average force that the hammer exerts on the nail? It's kind of similar to everything we've been talking about, I mean, lately in these problems, guys. So what we're looking at is force equals delta P over delta T, and here we go again. The mass, you know, it's basically the same argument, guys. I mean, it's a very, very similar argument. We're talking about the mass, VF minus VI kind of thing, changing the momentum over delta T. There's a number of ways we can play that. 5 is the mass of the hammerhead. 25, negative 25 going down, positive 25 going up. Do the subtraction. If they're going in opposite directions, that's a real big change in velocity. Don't call it 0. One's 25, and the other one's negative 25. Make sure that's straight. And they're saying the whole process is taking 0.150. So there we go. F is 1666.67 newtons. So we have that. Number 19, you need caution, I guess, when we do this, guys. See what we can say. For number 19, they say a mass small m, 20 kilograms, is connected as shown by a light cord, massless cord, to a mass big M of 35 kilograms, which slides on a frictionless horizontal table. The pulley has moment of inertia, I, of 0.3 kilograms meters squared, rotates about a frictionless axle, but it does have a moment of inertia. It's not like the pulley is not massless. The pulley has a moment of inertia. The moment of inertia I is 0.3 kilograms meters squared. It rotates about a frictionless axle and has a radius, capital R, of 0.10 meters. The cord does not slip on the pulley. What is the magnitude of the acceleration of small m? So they're saying some stuff here. I want to look at it. I mean, it's kind of, here's big M, and they already told us what that was. The pulley, we need real caution with the pulley because it's not what we've seen in other places. Here's small m. This is big M. What is the magnitude of the acceleration of m? Well, it's the magnitude of the acceleration of small m is the same magnitude acceleration that big M is experiencing because they're tied together. So we need to be careful. Basically, there's a number of ways this can be looked at, and there's a lot there. So let's see what we can say about that, I guess. Exactly how I want to talk about what's going on here, guys. We can say that something's going on here. In other words, there's going to be a T2 and a T1, and the way this thing's going to get pulled, we'll say T2, we can say a bunch of things. Didn't really, got to be, I guess, extremely careful how we do this. There is T2 right here, and there's T1 right here, which is not as much. And there's a radius here, guys. That's the thing you got to watch out for. There is right here a radius big R. So there's a tug of war, which is won by T2. That one's not as big, and hopefully this looks like a longer vector. T2 looks like a longer vector than T1. That's kind of the goal here. The amount of torque is the difference between T2 and T1 times the radius of the pulley. That is going to be equal to the moment of inertia times the angular momentum, which is equal to, and the angular momentum, alpha, is going to be A divided by big R. There's a lot there. If you look at this, this is true, but this is also true. If you look at this, and then look at this, go with the two things that are in green right now, and then say, okay, let me multiply by big R on each side. Let me multiply by big R on each side, and I end up getting IA equals, multiply by big R on each side, right? So you got this. True. That is true. Let's talk. I mean, let's talk as much as we can about. If that's the case, they told us I was equal to 0.3. Don't know what A is yet, but they did tell me I was equal to 0.3. I don't know T2 and T1, so I don't know the difference between the two, but maybe I'll see something on that. They did tell me that the radius was, did they use centimeters, or, I mean, I just want to make sure I'm speaking their language, guys. It's 0.1 meters. So this is 0.1 The radius is 0.1 meters, just square it. If you tinker with this, 0.1 meters squared is 0.01. Divide by 0.01 on each side. That's 3/10 divided by 1 over 100, which is 30. So when you solve here, when you divide by 0.1 squared on each side, you end up getting 30A equals T2 minus T1. I wrote it in a little different order in the notes, but it's the same thing. So what can we say? I mean, I'm trying to piece this together a little bit, guys. It's I guess it's easier done on paper, but it's easier. Well, I mean, I'm not sure what's easier, what's not sometimes. But so we can look at it, get to here. T1 is ma. We know that T1. Remember Newton's third law. This is T1 also. Just like going up this way, this is T2. I wish I made the ropes longer, but we're doing Newton's third law to kind of look at this stuff and kind of get a feeling for what's happening here. So let's keep going, guys. Let's keep looking at this. We got this. I can write that in a number of ways. We also got this. T1 is pulling M1. How much? Well, T1 is pulling big M with an acceleration A. M times A is the tension. So if that's the case, see exactly where I'm getting that. For some reason here, I'm looking at, so, oh yeah, right, exactly. So what does that mean? Well, T1, this guy's 35 kilograms times A. Here's another one. Okay, what is going on here? Well, the other guy's a different story down here. This guy's, for this thing to move, you got an mg this way, and it's being fought by T2. So mg minus T2. So small mg minus T2. Mg defeats mg. Small m defeats T2. Mg minus T2 is going to be small m times A. And absolutely. So let's see what the tension is. Why don't you multiply by the tension on each side? So let's see what we can do here, guys. It's a very, very fascinating problem, actually. Let me add T2 on each side and subtract MA. And that right there, mg is 20. 20 times 9.8 is 196. Small m is 20. Small m is 20 times 9.8. That's 196 minus 20 times A. Well, we got a lot of, we circled a couple things here. T2 is this. This is true. T1 is this. A lot going on here. I tell you what, let's take a good look at it. Maybe, and again, you'll see it with the notes too, guys, when we do this for 19. Let me kind of cut to the chase here. They said that T2 minus T1 is 30A. We also know that T2, this, minus T1, which is that, is 176 minus 20 minus 35, forgive me, 176 minus 20a minus 35a is 176 minus 55a. That's a huge move. If you took the T2 and the T1 and you went T2, which is this, T2, which is this, and T1, which is this, T2, which is this, and T1, which is that, and go T2 minus T1, you get this. We also know earlier that T2 minus T1 is this, 30A. Add 55A on each side. Add 55A on each side. It's 85A equals 176. Divide by 85 on each side. 196 divided by 85. That's something else. At the end of the day, it's what it is. It's 2.3 meters per second squared. Yeah, it's a hard one to get. It's not really hard, but it's certainly not easy. You really got to, these three make it happen. You take the T2 and you subtract T1 from it. Well, T2 is this. And T1 is that. Do the subtraction, you get this. T2 minus T1, they told us, was this. So put that there, then solve it. That is a great problem. That is a great problem. From here on in, it goes relatively smoothly. So let me, again, I erased a couple things, but you do have the notes. I forget we do have this on film, so you can always go back. So it's not really an issue that I'm going to take this stuff out. Now, we already know a lot of stuff. They gave us a lot of stuff. We solved a lot of stuff. Okay, there's a lot there, guys. I mean, a lot there, but we can do it. For number 20 and 21, they stay with this problem, which we're in pretty good shape if they do, because we just did the hardest part of this thing. What is the tension in the cord where big M is pulled? That's T1, right? T1 is M times A. It's 35 kilograms times 2.3 meters per second per second. That's it. Not bad. Once we got that acceleration, guys, we're looking pretty good. That's 80.7 newtons. Absolutely. That's 20. Was it 80.7? Yeah, right, 80.7, sure. 21, what is the tension in the cord where small m is pulled? So the tension in the cord where big M was pulled was this. And we did this earlier. We were playing this game earlier and we got it. For T1, what is T1? What is the tension where the big mass is pulled? Capital M, big M times A will give you T1. Yeah, we got it. 21 is saying, what is the tension in the cord where small m is pulled? Well, we said that T2 was that interesting situation where, it's kind of, there's the fall down, so there's mg minus ma. There's a lot you can say here. The mg was what? Was 20 times 9.8, which is 196. This is 20 times A. A was 2.3. I don't know why I erase these sometimes, guys. They don't look as good after the erasure. 4.6, 46, yeah, comes out pretty conveniently. I mean, it comes out to 150 newtons. Notice there is a difference. T2 is a bigger force. It's 150 newtons compared to 80.7 newtons. Yeah. The second one wins the tug of war. T2 is the second one. What is the tension in the cord where small m, what is the tension in the cord where small m is pulled? Yeah, absolutely. The way we had done this earlier, guys, was a number of things. I mean, we had done, but so it was pretty rough to begin this thing. But we knew that T2 had to be the one that's winning it, and T2 is saying, what is the tension in the cord where small m is pulled, or where small m is pulled? Well, small m is being pulled. But big M is also being pulled, So I mean, we're doing Newton's third law. The T2 with Newton's third law has to be bigger because it's rotating the pulley in a clockwise direction. So that's the way it's going to work. All right, guys, that is 21. That leaves us with 22, 23, 24, 25. That should go pretty smoothly. Let me just clear this a little bit. Okay, folks, let's continue. Let's finish up exam number 2, practice. Let's finish the last 4 problems, 22, 23, 24, 25. 22 pertains to buoyancy. An object weighs 7.84 newtons when it is in air and 6.86 newtons when it is immersed in water of density 1,000 kilograms per cubic meter. What is the density of the object? Well, the density of water is 1,000 kilograms per cubic meter. To find the density of the object, we kind of take into account that the object is going to weigh less when it's immersed in water. And that means something. Its density, pertains to what goes on here in the whole process. So I guess what we're going to look at, let's try to look at it. We know that the buoyant force, force buoyant, is the density of water, which we know, which we were told, the g of the Earth's gravitational field, and the volume of the object that is immersed, in this case, that is immersed in water. Well, the buoyant force is, here's what it would weigh outside of water in the air, so for our purposes, no buoyant force. And when there is a buoyant force, it weighs 6.86. So the difference between the two is the buoyant force. 1,000 kilograms per cubic meter, the density of water, 9.8 meters per second, and the volume of the object. So, I mean, there's a lot can be said here. Well, let's just keep going. Let's subtract right here, and we got 0.98. Here we got 1,000 times 9.8, 9,800. And V of the object, let me just write it OBJ, I mean just abbreviate that a little bit. We've got this. It's a lot to be said here. I mean, we can just find we can just find the volume of the object. Go 0.98. Just divide by 9,800 on each side. V of the object is pretty interesting. I mean, it's going to be 1 times 10 to the negative 4 meters cubed. Well, we answered a question that we weren't asked, but it's still a neat answer. It's still a neat process to even get that. What is going on here? You know, what is the density of the object? Well, the density of the object is the mass of the object divided by the volume of the object. So we did need to find the volume of the object. The mass of the object is what it weighs in air in newtons divided by 9.8. Weight divided by 9.8 will give you the mass. That's the mass divided by the volume of the object. At the end of the day, the density of the object that's 22, you guys. 23. 23, they're saying a natural gas pipeline with a radius of 0.3 meters delivers 8 cubic meters of gas per second. What is the flow speed of the gas in the pipeline for 23? Say that again. A natural gas pipeline with a radius of 0.3 meters delivers 8 cubic meters of gas per second. What is the flow speed of the gas in the pipeline? Well, you can look at that a number of ways. At least from different perspectives, but you're doing the same thing each time. The quantity per unit time, the flow rate, we'll call it Q. And a Q, you know, there's different kinds of symbols we can use, folks, but let's call this Q, the flow rate. Volume per unit time. Volume per unit time is, there's a lot, well, let's say that. I mean, let's just say that. It is the volume per unit time. The volume is A times some length divided by time. Well, the length divided by time is V, so you got Q is equal to, that's V, so it's got A times small v, which is velocity. This right here is volume. Divide by A on each side. You got Q over this. They're telling us that the flow rate is 8 cubic meters per second. The area, the cross-sectional area under consideration is pi r squared. The r is the 0.3. And that's it. I mean, you work. I mean, different ways you can look at this. Slight variations of looking at this whole process, but the whole thing is the velocity is 28.3 meters per second. And that's 23. 24. Two disks, A and B, rotating about the same axis. Let's talk about those. For number 24, two disks, A and B, rotating about the same axis, are brought together without the aid of any external torques. So they're rotating about the same axis. There's two disks, A and B, rotating about the same axis. They're brought together without the aid of any external torques so that they rotate as a single unit while they remain on the same initial axis. Initially, disk A rotates at negative 35 radians per second with a moment of inertia equal to 25 kilograms meters squared, and disk B rotates at 80 radians per second with a moment of inertia of 15 kilograms meters squared. So disk A has a moment of inertia of 25 kilograms meters squared. Disk B has a moment of inertia of 15 kilograms meters squared. After the union, what is the angular velocity of the single unit composed of the two disks? They do tell us that disk A has a negative rotational velocity, negative angular velocity. Disk A has negative angular velocity, disk B has positive angular velocity. Doesn't matter which one you call which, just know that they're going in opposite directions. You can essentially arbitrarily choose which one you're going to call the positive angular velocity and which one you're going to call the negative angular velocity. Just know that they're rotating in opposite directions before they get together. And what happens after they get together is whatever's going to happen. So for 24, let's take a look at some of the stuff that we could say related to that. So, I mean, there's a good number of things being said here, guys. So let's figure out how we want to look at this. I mean, there's disks A and B. Initially, disk A rotates at negative 35 radians per second. And it has a moment of inertia equal to 25 kilograms meters per second. Okay, and then disk B rotates initially. I'm not sure exactly. I have to look back in my answer key how exactly I'm writing some of the variables. But right now, let's just write this, at least get an idea, some sense of what we're doing here. And that one has a moment of inertia of 15 kilograms meters squared. Okay, so some stuff's being said here, guys. Let's see exactly how we wrote that. Yeah, the way I had written it, I just, I kind of abbreviated it a little bit. I said omega A is the initial rotation rate, initial angular velocity of A. Initial angular velocity of A is just omega A. Initial angular velocity of B is omega B, and then omega is going to be the end after you bring them together. This is certainly true what I wrote here. To kind of be consistent with the notes, you guys, let's just say, okay, these are the initial, and certainly true, certainly true. Let me just write it the way you're going to see it in the answer key as well. Again, all these answer keys in all three of the films that are review, all three of the films that constitute altogether in their totality, in their synthesis, all three of the films constitute a review for the final exam, as we said. At the end of each one of these three films, there is the entirety of exam number 1, exam number 2, exam number 3, how it looks, and the solutions to exam number 1, exam number 2, exam number 3. So I'm just trying to kind of stay consistent with what you're going to see there. These are the initial values. Omega, just plain omega is going to be the omega at the very end of what's going on. So there is the idea that the initial angular momentum equals the final angular momentum. I sub A omega A plus I sub B omega B. Add those together. They are a vector sum because one's called positive. One's associated with a positive angular momentum. One's associated with a positive, not only positive angular momentum, but a positive angular velocity. So one's associated with a positive angular velocity, one's associated with a negative angular velocity. So we got this, and then we got together what happens? Well, together they become a new moment of inertia. That's the sum of the moment of inertias times the end. And that's the end. That's what we want to find out. We want to find out what's going on there. Well, if you want to solve for omega, go ahead and do so. Let's do it without using numeric symbolism, without using explicit numeric symbolism. Just divide by the quantity I sub A plus I sub B on each side. You got I sub A omega A plus I sub B omega B over I sub A, I sub B, looking something like that. Well, okay, that's what it's looking like. That's what we're doing. If that's the case, plug in what you know. I mean, I sub A is 25. Omega sub A is negative 35. I sub B is 15. Omega sub B is 80. I sub A and I sub B is essentially, the 25 and the 15. 25 and 15, you got 40. That's it. That's as simple as that. You grind that out, you got the answer. Omega is 8.125 radians per second. Okay, sounds good. That's 24 from exam number 2. 25, how much kinetic energy was lost in this collision? Well, I guess when you bring them together, it is a collision. We do know that linear and angular momentum are always conserved. That doesn't mean that kinetic energy is always conserved, because it's not. Energy in general is always conserved. Linear momentum is always conserved. And angular momentum is always conserved. Absolutely. We've said that. True. So what are we going to do about it? Well, how much was there a loss of kinetic energy? I think there's a way we can easily find that out. I mean, and that's essentially stuff we've done in the past. I mean, you look at it and say, okay, well, how much kinetic energy was initially present in the system? Our thought is you're certainly not gaining kinetic energy. So let's see what does happen. For 25, you're basically saying, okay, initially the situation is 1/2 I omega squared, 1/2 I sub A omega sub A squared, plus 1/2 IB omega sub B squared. That is all the kinetic energy that is initially present in this rotating system. After they link up, you have 1/2 I, but the I right now is this conglomeration, I guess you could say, this unity of the two I's times the omega squared that we just figured out what it was. Well, guys, this becomes a relatively simple exercise. This is going to be the delta, the change in kinetic energy. The kinetic energy that was lost is going to be this. You plug in the numbers here. I mean, you basically just say 1/2 I sub A, I sub B. Now, it doesn't matter the direction it's going. When you square it, it's going to be positive. Doesn't matter the direction it's going. When you square it, it's going to be positive. Here's the I sub B. Here's the omega sub B. Here's the omega sub A squared. Here's the omega sub B squared. Yeah, absolutely. And then minus 1/2 the 25 and the 15. The I sub A and the I sub B add up to 40. And we said it was 8.125. What the new omega is. Square it. Okay, grind out the numbers, folks. We are talking about 61,992 joules, which is roughly equal to 62,000 joules. Again, always work under the assumption that we're not going to worry about significant figures. Assume that everything, all the numbers are absolutely true, completely true. Well, that got us through Physics 120, exam number 2, fall 2019 practice exam. We've already done, we've already looked at Physics 120, exam number 1, fall 2019, and now we just looked at Physics 120, exam number 2, fall 2019. And now we got Physics 120, exam number 3, fall 2019 to look at as well to finish it out. All 3 exams will be in different, we'll have 3 separate films, one for exam number 1, one for exam number 2, one for exam number 3. At the end of all of them, at the end of each of them, however, all of the solutions, all the exams themselves, the way they look back then, and their solutions, all of them will be present at the end of film number 1, just for exam number 1. All of the solutions for exams 1, 2, and 3 will be there, as will be the case in the film for exam number 2, this one, as will be the case for exam number 3. All right, we'll take a look at exam number 3 real soon. Take care.